right, everyone. Get ready for a deep dive today.
Yeah.
Into the world of GIS.
Yeah, GIS.
Geographic Information Systems.
Oh.
For those of you who are like, what is that?
Right.
So, think navigation apps.
Yeah.
Think how scientists can track, like, deforestation, all that good stuff.
Yeah.
And today we're going straight from the source, so to speak.
Okay.
I watched a really awesome YouTube crash course by a GIS expert.
Right.
And I'm basically working from the notes from that crash course.
Nice.
So you're getting, it's curated, it's consolidated, it's
the best stuff.
all the best parts.
The best.
And you're going to sound so smart after this.
You're going to be dangerous.
Yeah.
With all this knowledge.
Sick, yeah.
GIS. It's really cool.
Okay.
It's like a superpower for understanding our world.
Ooh.
It's not just about maps anymore.
Okay.
It's about using location data to answer questions.
Okay.
And solve problems in ways we never could before.
I am intrigued. But for those of us who are like brand new to this,
right?
What exactly is GIS?
So imagine you're trying to plan like a cross-country road trip.
Okay.
But you don't have a map.
That sounds terrible.
Right.
Yeah.
It would be pretty tough.
Yeah.
So spatial data is essentially like a map.
Okay.
But instead of just showing you roads and cities,
Mm-hmm.
it tells you things like elevation,
Okay.
traffic patterns,
Well, yeah.
even the location of like the nearest gas station with the cheapest snacks.
Okay, now you're speaking my language, cheapest snacks.
Right.
But you're saying this data goes way beyond just like showing us where stuff is.
It does. It does.
It's telling us like what those things are,
right.
how they maybe relate to each other.
Exactly. Exactly.
Okay.
That's where the magic of GIS comes in.
Okay.
Combines two key elements, geometry and properties.
Geometry and properties.
Yeah, so geometry is all about the shape and location of things.
Yes.
Think points, lines, and polygon.
Okay, I'm picturing like those connect the dot games from when I was a kid.
Yeah.
But like way cooler.
Way cooler. Yeah, instead of cute animals, we're mapping out like the entire planet.
Okay, all right, so give me some real world examples.
Okay, yeah. So think of cities as points on a map.
Okay.
Roads as lines,
Mm-hmm.
and maybe the outline of a national park as a polygon.
Okay, I'm with you.
But here's where it gets even more interesting.
Okay.
Each of those geometric shapes can have properties attached to it.
Properties, like what kind of properties are we talking about here?
Okay, so let's stick with that national park example.
Okay.
The polygon that defines its boundaries could also have properties like its name, the types of ecosystems it contains.
Oh, wow.
The number of visitors it gets each year.
Okay.
Or even like the best trails for spotting wildlife.
Okay, so it's not just about location.
Right.
It's like a whole universe of information tied to those locations.
Precisely.
This is so cool.
Uh-huh. Yeah, and there are different types of spatial data, each with its own strengths.
Okay.
So you got vector data.
Vector data. Okay.
It uses those points, lines, and polygons we just talked about.
Okay.
It's really good for representing clearly defined features like roads or buildings.
So if I wanted to map out
Yeah.
all the best taco trucks in my city,
Yes.
that would be vector data.
Absolutely. You got it.
What else?
Okay, let's say you wanted to track changes in forest cover over time.
Okay.
That's where raster data comes in.
Raster data.
Yeah, it's like a digital photo made up of pixels.
Okay.
Perfect for representing continuous data like elevation or temperature.
So like satellite images showing deforestation in the Amazon?
Exactly. That's a perfect example.
Ooh, okay.
Yeah.
So raster's like the big picture,
Mm-hmm.
and vector is kind of like the finer details.
Exactly.
Okay, I'm with you.
Yeah.
So how is all this information stored? Are we still using those giant paper maps from, like, libraries?
Oh, no, no, no. Well, paper maps still have their place, of course.
Yeah.
But digital storage is where it's at for GIS.
Okay.
There are tons of different file formats.
Yeah.
Some are more technical than others.
Okay.
But one you might come across is the shapefile.
A shapefile.
Yeah, you can think of it as a container that holds all the geometry and properties for features, like roads, rivers, or even like the boundaries of your favorite pizza delivery zones.
Now that's a map I would use.
Right.
Pizza delivery zones.
Important stuff.
Yeah. Okay, so it sounds like we're dealing with
Yeah.
massive amounts of data.
We are.
How do we even manage all that?
That's where databases come in.
Database.
Yeah, they're like super organized filing cabinets
Okay.
for spatial data. So they allow us to store, manage, and query vast amounts of information.
Like Google Maps.
Exactly.
Yeah.
Great example.
Yeah.
Google Maps is constantly pulling data from massive databases.
Just show you real-time traffic updates.
Yeah, and to navigate you through all the chaos of rush hour.
Okay, so now we're getting into, like, the real nitty-gritty of how GIS works.
Yeah.
We've got the data down. We know how it's stored.
Right.
But how do we actually, like, interact with this data and make sense of it all?
Well, that's where the fun begins.
Okay.
You know, those superpowers we talked about earlier.
Yeah.
That's where GIS software steps in.
Oh.
It's the toolbox that allows us to unlock the true potential of spatial data.
Okay.
But before we jump into the tools, it's important to understand that GIS is more than just software.
Okay.
It's also a whole field of study called Geographic Information Science.
Ooh, fancy.
I know, right?
So it's like GIS is the doing.
Yeah.
And Geographic Information Science is like the thinking behind the doing.
You could say that.
Okay.
Yeah. Geographic Information Science really explores those theoretical foundations, analytical methods, and ethical considerations of working with spatial data.
Okay.
But let's not get too bogged down in theory.
Okay, yeah.
Let's talk about what you can actually do with GIS software.
Yes, please give me the practical stuff.
Okay, so for starters,
Yeah.
you can view and analyze data
Great.
in ways that would be impossible with traditional maps.
Oh, okay.
So imagine layering data on population density with crime statistics or environmental hazards.
Gotcha.
Suddenly, you can see patterns and relationships that were hidden before, which can help you make better decisions, whether you're a city planner, a public health official, or even just a curious citizen.
I like that, a curious citizen.
Right.
All right, so GIS software helps us see the world in new ways. But can we actually create new data using these tools?
Absolutely. Absolutely.
Right.
You can digitize features from satellite images.
Oh, wow.
Draw new shapes based on field observations, or even analyze existing data to derive new information.
Wow.
Yeah. So imagine a team of archaeologists using GIS to map out the ruins of an ancient city.
That's amazing.
Or a group of biologists tracking the movement of endangered species.
Like, we're not just mapping the world.
Right.
We're, like, shaping it with data.
Exactly. Exactly.
That's pretty powerful stuff.
Yeah, and of course, you can create maps.
Oh, yeah.
Detailed interactive maps that communicate your findings in a way that's easy to understand and visually compelling.
Makes sense.
But, you know, maps are just one output of GIS.
Right.
It's the analysis and insights that really make it powerful.
Yeah. Okay, so we're seeing data in new ways.
Yeah.
Creating new data, making awesome maps. What else could this GIS software do?
Well, one of the most exciting aspects is spatial analysis.
Spatial analysis.
Yes, this is where we get to the heart of what makes GIS so powerful.
Okay.
Finding patterns, understanding relationships in space, and making predictions based on location.
Okay, give me an example of this spatial analysis magic.
All right. Imagine you're a city planner, and you're trying to decide where to build a new school.
Right.
Using GIS, you can analyze data on population density, existing schools, traffic patterns, and even the availability of green spaces to find the optimal location.
Gotcha.
You could even model how different school locations would impact traffic flow or student commutes.
So we're not just like throwing darts at a map anymore.
No.
We're using data to make smarter decisions.
Exactly. Data-driven decisions.
I like it.
Yeah.
Okay, impressive.
And then there's data transformation.
Data transformation.
It might sound a bit technical, but it's essential for integrating information from various sources.
Okay.
So imagine you're working with data from different government agencies, each using its own file format, and coordinate system data transformation tools help you wrangle all that data into a compatible format.
Gotcha. So you can actually analyze it.
So it's like being a digital detective, right?
I like that.
Piecing together clues from all these different sources to solve the mystery.
I love that analogy, yeah. Data transformation is all about making sure your data plays nicely together so you can extract meaningful insights.
Okay. I am starting to get why GIS is such a big deal.
Yeah.
We've covered like a lot of ground here, from the basics of spatial data to the power of GIS software.
Yeah.
But I have a feeling we're just like scratching the surface.
Oh, yeah.
What other adventures await us?
Well, now that we have a good grasp of the fundamentals, it's time to tackle one of the most important
Okay.
and often misunderstood aspects of spatial data.
Yeah.
Projections.
Okay, buckle up, everyone.
Yes, buckle up.
Things are about to get three-dimensional.
We're going 3D. Okay, so remember how we've been talking about how powerful GIS is for understanding our world? Well, there's a catch, right?
Okay.
Our planet is a sphere.
And most of our maps and screens are flat.
Yeah.
So that's where projections come in. Just like translating a 3D world onto a 2D surface.
I'm already feeling a bit lost. Like, how do you...
challenge.
Yeah, how do you begin to, like, wrap a basketball on a piece of paper?
Right, exactly.
Without getting any wrinkles.
So it's a good question, and it's something that, map makers have been grappling with for centuries.
Yeah.
The simplest model is to just treat the Earth as a perfect sphere.
Sure.
It's the decent starting point.
Yeah.
Especially when you're zoomed out, looking at the whole world.
Right.
But the Earth isn't actually perfectly round, is it?
No, it's not. And I vaguely remember something from, grade school about the Earth being a bit squashed, like a grapefruit.
You're exactly right.
Okay.
We call that shape an ellipsoid.
Ellipsoid.
Yeah. Think of it like a sphere that's been slightly flattened at the poles.
Okay.
And bulges at the equator. It's more accurate than a simple sphere.
Yeah.
Especially when you need precise measurements for things like surveying or navigation.
Makes sense.
Now, isn't there an even more accurate model?
Yeah, something about a geoid.
You're on fire today.
Okay.
The geoid is the most accurate representation we have.
Okay.
And it's based on the Earth's gravity field.
Okay.
So imagine the Earth's surface is covered in water.
Okay.
The geoid represents the shape that water would take, factoring in all the bumps and dips caused by mountains, valleys, and even variations in the Earth's density.
So it's like a super detailed gravity-powered map of the Earth's, true shape.
Yes.
That's amazing.
It is really cool.
But also sounds incredibly complex.
It is.
Do we really need to get that detailed for most GIS applications?
It's true that the geoid is pretty complicated to work with mathematically. So for most everyday uses, we stick with ellipsoids. They strike a good balance between accuracy and practicality.
Makes sense.
But the key takeaway here is that we need a way to align our maps and data with whichever model we're using.
Okay.
That's where datums come in.
Datums.
They act like anchors, connecting our maps to a specific reference point.
Okay, so a datum is like setting the stage for our map.
Exactly.
Making sure everything's in the right place.
Exactly. Yeah, you got it.
Okay.
So there are global datums like WGS84.
WGS84.
Which is what's used by GPS systems worldwide.
Okay.
It's a good general purpose datum.
Yeah.
But sometimes we need to be more precise.
Okay.
That's where local datums come in.
Local datums.
They're tailored to fit specific regions.
Okay.
Minimizing distortions.
Okay.
And improving accuracy for local mapping projects.
So you're saying that using the wrong datum could actually mess up my measurements?
Absolutely.
By a lot.
By a lot. Yeah. Remember that Nandi Hills example from the notes? There was a difference of 85 meters in elevation.
Oh, wow.
Depending on which datum was used.
That's huge.
That's like the height of a 20-story building.
Yeah.
So imagine the problems that could cause if you're building a bridge.
Oh, yeah.
Or planning a hiking route.
Yeah, okay. I'm starting to see why this matters.
Right.
Choosing the right datum is like making sure you're speaking the same language as your data.
Exactly. Exactly.
Okay.
And once we've got our datum sorted out, we need a system for actually pinpointing locations on our map.
Right.
That's where spatial reference systems come in, or SRS.
SRS. Okay, another acronym.
I know there are a lot of acronyms in GIS.
GIS glossary is getting pretty long.
It is. But SRS, they're like the rules of the game.
Okay.
Defining how we measure distances, calculate areas, and specify coordinates.
Okay, break it down for me. What are the main types of spatial reference systems?
Sure, so there are two main types.
Okay.
Geographic Coordinate Systems, or GCS, and Projected Coordinate Systems, or PCS.
Okay, now I'm really feeling like I'm back in geography class.
Right.
Remind me, what's the difference between those two?
Yeah, so a GCS uses latitude and longitude to define locations on the Earth's surface.
Okay.
Just like you'd see on a globe.
Right.
It's a universal system.
Yeah.
But it has one major drawback.
Okay.
It treats the Earth as a sphere.
Right, which we know is not entirely accurate.
Exactly.
Okay, so we need a system that takes that ellipsoid shape into account.
Yes.
Is that where projected coordinate systems come in?
Exactly. A PCS projects those latitude and longitude coordinates onto a flat plane using a specific map projection.
Okay.
It's like taking that 3D globe and flattening it out into a 2D map.
Right. Which brings us back to, like, the whole orange peel analogy.
Yes.
Okay, so projections are essentially the mathematical magic that allow us to represent a round Earth on a flat surface.
Yes, you got it.
But I thought you said no projection is perfect.
Right.
There's always some kind of distortion.
You are absolutely right.
Okay.
Every projection involves trade-offs because you can't perfectly preserve all the properties of a sphere when you flatten it.
Yeah.
It's like trying to make a perfect pizza.
Okay.
No matter how you slice it, there's always going to be some crust that's a bit thicker or thinner than the rest.
I like that analogy.
Yeah.
Okay, so how do we choose the right projection?
Yeah.
Is there like a secret formula or something?
I wish there was.
Yeah.
Unfortunately, there's no one-size-fits-all solution.
Okay.
The best projection depends on the specific map you're creating.
Okay.
And the properties you want to prioritize.
So it's a bit of an art as well as a science.
Exactly. Exactly.
Okay.
So think of it like choosing the right tool for the job.
Okay.
There are conformal projections which preserve shapes and angles, making them great for navigation charts.
Makes sense.
But they tend to distort areas, especially at higher latitudes.
Ah, so that's why Greenland looks so huge on some maps.
Exactly. Exactly. Right. Then you've got equidistant projections, which are all about preserving distances from a central point.
Yep.
They're great for things like flight planning or calculating the range of a radio signal.
So if I wanted to figure out the shortest route to fly from New York to London, I'd use an equidistant projection.
You got it.
Okay.
And finally, there are equal area projections.
Equal area.
Which, as the name suggests, prioritize preserving the relative areas of different features.
Gotcha.
They're great for thematic maps, showing things like population density or land use.
So conformal for shapes.
Yeah.
Equidistant for distances. Yeah. Equal area for areas.
You got it.
I think I got it.
Yeah.
But if I had to choose, like, the best projection...
Oh, the classic question.
Which one would it be?
The truth is, there is no single best projection.
Okay.
It all depends on what you're mapping. Okay.
And what you want to emphasize.
So it's like choosing the right spice for your dish.
I like that.
It all depends on what kind of flavor you're going for.
Exactly. You want that little kick.
Yeah.
So that table in our notes provides a good starting point for choosing projections based on different map types.
Right.
It's all about understanding the strengths and weaknesses of each projection. And selecting the one that best suits your needs.
My brain is starting to feel a bit overloaded with all this talk of projections and datums.
It's a lot. It's a lot.
And can we take a step back and just like remind ourselves why this all matters?
Of course. So understanding projections and datums is crucial for working with spatial data. Because it affects how we measure distances, calculate areas, and even perceive the relationships between different features on a map. So if you're using the wrong projection or datum, your analysis could be skewed,
leading to inaccurate conclusions and potentially even dangerous decisions.
Oh, wow. Okay. High stakes.
Those stakes,
Okay. I'm starting to see the bigger picture here.
Yeah.
It's like before we can even begin to analyze spatial data, we need to make sure we're all speaking the same language.
Exactly.
Using the same reference points, understanding the limitations of the tools we're using.
Yes. It's all about setting the stage for accurate and meaningful analysis.
Well, I feel like we've climbed Mount Everest of GIS knowledge today.
We have. We've gone from the basics of spatial data to the complexities of projections and datums.
I'm exhausted. But also kind of exhilarating.
I know what you mean.
Yeah.
It's a lot to take in.
It is.
But it's also incredibly fascinating. And the best part is we're just getting started.
Oh, no.
I know.
There's more.
There's more.
Wow. I feel like we just, completed a crash course in cartography.
I know, right?
Who knew there was so much to learn about maps and data?
It's amazing how much complexity there is.
Yeah.
Hidden beneath the surface of those seemingly simple maps.
Yeah. Like I said before, this deep dive.
Yeah.
I kind of just took maps for granted.
Right.
But now I'm, really seeing them in a whole new light.
Literally.
Literally, yeah. I'm starting to notice the different projections, the way the data is represented, just the subtle choices that map makers are making.
It's true.
That can shape, our understanding of the world.
It's like you've unlocked a secret code.
Yeah, it's like a secret code.
Yeah.
And the more you learn about GIS,
Yeah.
the more you start to see its fingerprints everywhere.
It's true.
It's in our navigation apps. It's in our weather forecasts.
Yeah.
Even in like how we choose where to live.
Right.
Or where we go on vacation.
Yeah.
Like GIS is silently shaping our world in countless ways.
In so many ways, yeah.
Yeah.
And you know what I find really exciting is how accessible GIS is becoming. It's no longer just a tool for experts.
Okay.
There are tons of free and open source software options available.
Cool.
And online resources are making it easier than ever to learn the basics.
So anyone can become a GIS whiz these days.
Pretty much, yeah.
That's pretty cool.
It is really cool. It's really democratizing this technology.
Yeah.
Yeah.
I'm starting to feel like I could actually create my own maps now.
I bet you could.
Maybe a map of, like, all the best coffee shops in my neighborhood.
Okay. Yeah.
With, like, different symbols for each type of roast they offer.
That's a good idea. And you know what?
What?
That's exactly how a lot of people get started with GIS. They have a question they want to answer or a problem they want to solve.
Yeah.
And they realize that maps and spatial data can help them find a solution.
It's like having a superpower for understanding your surroundings.
It really is. It's like this lens you can put on to see the world in a different way.
I'm already, like, thinking of all these different ways I could use GIS in my everyday life. Yeah.
Maybe I could map out the safest bike routes to work.
Yeah.
Or, like, find the best places to stargaze.
That's a good one.
Based on light pollution data.
You could do that. Absolutely.
That's so cool. And that's just, like, the tip of the iceberg.
Oh, yeah.
The possibilities are truly endless.
They really are.
I mean, whether you're interested in, like, urban planning, environmental science, public health, history, or even just exploring your own backyard.
Right.
GIS has something to offer.
It really does.
I have to say, this deep dive has been such an eye-opener.
Yeah.
I came in thinking it was all about maps.
Right.
But I'm leaving with, like, a whole new appreciation for spatial data.
Yeah.
And how it can help us make sense of the world around us.
And that's what it's all about, right?
Yeah.
Using data to understand our planet, solve problems, and make better decisions.
For anyone listening who's feeling inspired to learn more, where should they start?
There are so many great resources out there.
You can check out online courses,
Okay.
explore open source software options, or even just start playing around with Google Maps and see what you can discover.
Right.
The important thing is to just dive in and start exploring.
I love that. And remember, you don't need to be a cartography expert to appreciate the power of GIS.
You don't.
It's a tool for everyone.
It is.
And the more people who understand it, the better equipped we'll be to face, like, the challenges of the 21st century.
Couldn't agree more.
So there you have it, folks.
Yeah.
A crash course in GIS.
From spatial data and software to projections and datums.
We hope you enjoyed this deep dive.
We did.
And we encourage you to keep exploring this fascinating world of maps and data.
Until next time.
Happy mapping.
Happy mapping.